The shallow water equations are a set of hyperbolic partial differential equations that describe the flow below a pressure surface in a fluid. The shallow water equations can also be simplified to the commonly used 1D Saint-Venant equation. The equations are derived from depth integrating the Navier-Stokes equations. In the case where the horizontal length scale is much greater than the vertical length scale, under this condition, conservation of mass implies that the vertical velocity of the fluid is small. It can be shown from the momentum equation that vertical pressure gradients are nearly hydrostatic, and that horizontal pressure gradients are due to the displacement of the pressure surface, implying that the horizontal velocity field is constant throughout the depth of the fluid. Vertically integrating allows the vertical velocity to be removed from the equations. The shallow water equations are thus derived, while a vertical velocity term is not present in the shallow water equations. Note that this velocity is not necessarily zero. This is an important distinction because, for example, the vertical velocity cannot be zero when the floor changes depth, and thus if it were zero, only flat floors would be usable with the shallow water equations. Once a solution has been found, the vertical velocity can be recovered via the continuity equation. Situations in fluid dynamics where the horizontal length scale is much greater than the vertical length scale are common, so the shallow water equations are widely applicable. They are used with Coriolis forces in atmospheric and oceanic modeling, as a simplification of the primitive equations of atmospheric flow. Shallow water equation models have only one vertical level, so they cannot directly encompass any factor that varies with height. However, in cases where the mean state is sufficiently simple, the vertical variations can be separated from the horizontal, and several sets of shallow water equations can describe the state. Equations. Conservative form. The shallow water equations are derived from equations of conservation of mass and conservation of linear momentum, which hold even when the assumptions of shallow water break down, such as across a hydraulic jump. In the case of no Coriolis, frictional or viscous forces, the shallow water equations are: here eta is the total fluid column height, and h is the water depth if the surface is at rest. The 2D vector is the fluid's horizontal velocity, averaged across the vertical column. G is acceleration due to gravity. The first equation is derived from mass conservation, the second two from momentum conservation. Since velocities are not subject to a fundamental conservation equation, the non-conservative forms do not hold across a shock or hydraulic jump. When we include also the appropriate terms for Coriolis, frictional and viscous forces, we obtain, where it is often the case that the terms quadratic in the U and V, which represent the effect of bulk advection, are small compared to the other terms. This is called geostrophic balance, and is equivalent to saying that the Rossby number is small. Assuming also that the wave height is very small compared to the mean height, we have wave modeling by shallow water equations. Shallow water equations can be used to model Rossby and Kelvin waves in the atmosphere, rivers, lakes and oceans, as well as gravity waves in a smaller domain. In order for shallow water equations to be valid, the wavelength of the phenomenon they are supposed to model has to be much higher than the depth of the basin where the phenomenon takes place. Shallow water equations are especially suitable to model tides which have very large length scales. For tidal motion, even a very deep ocean may be considered as shallow, as its depth will always be much smaller than the tidal wavelength.